Welcome everyone to another episode of the Shannon channel. Today it's a different time because we have a speaker, which is Sidharth Jaggi from Hong Kong, and he's gonna give us a talk on Shannon-Style Theorem for Adversarial Channel. Thanks, Sid.
Thank you for the invitation, Salim, and thank you for making the adjustment to the Hong Kong time. So happy to talk about this stuff that I'm quite excited about. Let me share my screen. Here we go. So I assume you can see the screen now.
Yes. Yeah.
All right. So yeah, this is joint work with my ex-student Nicholas Wong, my ex-postdoc Amitalok Budkule. He's faculty now in IIT Kharagpur in India, and Andrei Bogdanov, my colleague here at CUHK in the computer science department. So as is often the case, I'll take credit for a bunch of ideas from other people, yeah, but again, credit where it's due to these folks. So let's dive into it. And by the way, I know, of course, your style, Salim, is to interrupt with a bunch of useful questions, which is always great. You should do the same, Marco, Rabad, and anyone else who joins at any point, right? So that's all good. All right. So I like to think of this topic, adversarial channels, as a nice intro to a whole bunch of different ideas. Like, to paraphrase Dr. Strangelove, if you've seen the movie, it's how I learned to stop worrying in love, probability, combinatorics, like a whole bunch of different topics, information theory, of course, coding theory. And if by the end of this talk we get to the very bad joke about being completely positive, then I will view this as a successful talk. Okay, so that is my personal goal, to make a bad pun. Before I dive into it, like typically the audience is most engaged in the beginning. So let me front load by just using a few slides to highlight a lemma, a technical lemma that will be useful later. Like, there'll be lots of pretty pictures in the rest of the talk, but if I can have the audience's attention for the first few minutes, this lemma, which I think is of independent interest, is quite interesting, useful, and I think novel, though there are connections with Affinity's theorem, exchangeability, and so on. All right. So the question is the following. So suppose someone gives you a target joint distribution. So someone tells you you want a particular joint distribution P of x comma x prime over the product alphabet x times x. Okay, and now the goal is to construct a long sequence of random variables such that every ordered pair xi xj has approximately this target distribution. Okay, so if you want to think of it geometrically instead of random variables, if you think of a bunch of points, so suppose someone gives you a particular distance roughly, and then asks you to construct a large object such that every pair of vertices have that distance. Like, that's a geometric analog, and indeed there's a connection between that question and this question about random variables. But that's the goal. Okay, so suppose someone asks you, is this possible? And there's what we can show is achievability and a converse. So in particular, if this target distribution here can be written as a convex combination of product distributions. I mean, this all that this PU is doing is it's taking a linear combination, it's taking a convex combination of product distributions. So if so, then you can construct arbitrary long such sequences. If these distributions are called completely positive distributions, they've been studied in convex optimization before, and so on. They form a convex set, that's also useful. And if not, if this target distribution is far from being completely positive, then you can only construct a constant, like a constant length such sequence. Okay, so I already see some people gazing at this pensively. This, I promise, is probably the most technical slide in the talk, but it's important. That's why I wanted to front load it and start off.
Sid, I've seen maybe for me similar result in CS where you want like every pair to be epsilon like quasi independent or something. Is this kind of like extending that result?
So independent is a very special case, of course, of a specific target distribution, right? And Yeah, so for independent, if the random variables you want every pair to be pairwise independent, then that's a special case, and this result will collapse in a certain.
Or within like an epsilon, like.
So you can always, of course, construct a whole bunch of independent random variables, right? You can just sample independently from an independent distribution, and then you'll have independent random variables. But now, suppose you want to generate something such that every pair has a specific pre-assigned correlation. Well, how would you do that? And not just correlation, but a specific joint distribution. Then how do you do that? And indeed, we have some other conjectures regarding this as well. So this is not fully understood, but at least this particular flavor we now understand, and it will tie together with the application in mind about adversarial channels. But I think this lemma is of independent.
And one quick question also. So if the joint distribution does not factor with including this auxiliary random variable, then you cannot do it?
Then you cannot have more than a constant number. So indeed, you can have a small number, but not more than a constant number.
Okay.
And that's the harder part of the proof. That's an impossibility result that I'll tie. The proof that we have is quite combinatorial right now. It relies on duality, Ramsey theory, and so on. So it's in very strong sense. It's related to a generalization of the Plotkin bound, which perhaps you've heard of. That's a bound on code sizes and so on, right? So we'll get there. That's the goal, to get there by the end of this talk. Okay. All right. Any other questions before I move on? So again, this is probably well, I don't know about the most technical slide, but at least I started again by being dense, and then I'll be a little bit light. Okay. All right. So so first of all, prologue. So Shannon, of course, everyone on this channel is a Shannon theorist, right? Well, maybe not everyone, but anyway, hopefully, if you've stumbled across this video, then you know who Claude Shannon is and his contributions to random noise, right? But this talk will actually have a different focus. But before understanding that focus, let's understand Shannon's contributions from a particular viewpoint, which will help see the difference with adversarial noise. Okay? So in a standard, let's say, random noise communication system, Alice has a message she wants to send to Bob over a noisy channel, which introduces some random noise, right? And the goal is usually to communicate a large message reliably over this random noise channel, right? Where large and reliably are put in quotes because they have specific meanings. So large means as high a rate as possible. Reliably means the probability of error should vanish, right? So as a specific example, Alice, for example, has some message M, which is some NR bits, right? N being the block length. And then the channel, if it's a bit flip channel, like a binary symmetric channel with crossover probability P, so P is the noise level. So sort of three parameters here are the rate, the noise level, and the block length. And then based on the noisy code word, Bob attempts to decode, right? So this is just an example, right? And if we demand a small probability of error, that is in some sense demanding that the decoding regions corresponding to, or that roughly speaking corresponds to requiring a soft packing of the code words. So imagine drawing noise balls around transmitted code words, and you want there to be not too much overlap between these noise balls, right? There's a tension, of course. You also want a high rate, so you want many code words. But if you're too greedy, if you try to pack too many of these, then there'll be too much overlap, and then your probability of error will be large, right? So that's one way of thinking about a Shannon type channel, right? Where some probability of error is tolerated, and the noise is random. Now Shannon's contribution in this example, but also of course in large generality, is to figure out the optimal dimension of soft packings, like asymptotically the correct exponent in the rate of the number of these balls you can pack, such that there isn't too much overlap. Right? So again, that's one way of viewing Shannon's contribution. Now, the focus of this talk is adversarial noise. It's worst case noise, and here things are really quite different. So even though this was in some sense posed almost contemporaneously by Hamming, as in parallel with Shannon's work, it went off in a very different direction. This tends to be something that perhaps computer scientists have looked at more closely than information theorists, but there are connections, right? And again, I mean, of course, even in information theory, like arbitrary varying channels, that literature has looked at it a lot, and that's the closest point of contact for us. So in that context, so in an AVC setting, arbitrary varying channel setting, how do we view it? So again, Alice has a message. She wants to send it to the decoder Bob. But now the channel, instead of having random noise, has adversarial noise, has a jammer. Okay, so this is James the jammer. He's going to put some noise. And now again, you want to communicate a large message reliably over this adversarial noise channel. And the challenge is that this jammer can, in principle, see everything that is being sent. So he sees the transmitted code word, and in fact knows the encoding function, so knows everything. He's omniscient, he can see everything. And the goal is to communicate reliably in such a setting, right? And this changes the problem drastically in many different ways, which we'll see. But before we do that, let's just put some notation over here. So, so again, there's a message with NR bits. This is encoded to some code word over some alphabet, say script X, with some power constraints. We'll see this later. I'll talk about this a little bit later. The jammer chooses a noise sequence or a state sequence, as it's called in the literature, in the AVC literature, arbitrary varying channel literature. And again, maybe there are some constraints. I'll talk about this again later. So, so think of it as Alice has some power constraint in some sense. James has a power constraint, and then the channel combines these two things: Alice's code word and James's noise sequence, and then generates a noisy code word Y, and then Bob is supposed to estimate the transmission. Okay. And again, this S can depend on the transmitted X. So that's going to be the challenge. So again, there are three things that sort of parameterize this problem: the input constraint, so Alice's input constraint. So, and again, I'll describe this in more detail later, but really it comes down to, you can think of it like a power constraint. So for example, in a binary input, binary output channel, maybe Alice is a bound on the number of ones in her binary code word, right? So that could be like a power constraint. Or in general, you could have a type constraint. You could have a type constraint on the code word here. Similarly, you could have a type constraint on the state vector. So a type, very roughly, for those who haven't seen this before, is just like the histogram of a vector, right? It's the empirical distribution of a vector, and maybe you have some constraints on the empirical distributions that are allowed. Okay? Again, we'll see this in more detail later. So these three things, the constraints on Alice, James, and then the way that the channel combines them, will define a problem, and we'll see this. So for example, suppose you could have something where the channel law, this channel law is going to be Y is equal to X plus S. So this is an example of a state deterministic channel law. That is, the channel output is a deterministic function of the two channel inputs, of Alice's input and then the noise sequence, right? So Y is a deterministic function of X and S. Another way of thinking about it is that the conditional distribution W of Y given XS is a deterministic function. It's a 0-1 function of the inputs X and S. Right?
Sid, a quick question. You may have mentioned it, but I missed it. So who knows the state?
So on a priori, only the jammer knows the state he chooses, right? So Alice, so yeah, let's back up a little bit. So in this thing, the problem is defined by these three things: Alice's input constraint, James's state constraint, and the channel law. These three things are known a priori to all parties. That is, like, for example, how much power Alice has, how much power James has, and the channel law. But given this, like, aside from that, Alice doesn't know anything. Okay. James gets to see the exact transmission and the code book. So nothing is hidden from James. Okay. And then he can decide how to jam. Alice and Bob, on the other hand, all that they know is the channel law and the code book that they designed in advance. Okay?
So, for example, I cannot think of a case where the decoder Bob can estimate the state, like if it's a channel state. That this is different. This is not.
So, I mean, he could try to estimate it, and maybe if James does something silly, then maybe he could, or maybe he couldn't. It's not clear. It would have to depend on the encoding decoding scheme.
Okay.
Yeah. Like, for example, just trying something where you put in a pilot sequence and hope that James flips the same number of bits in the pilot sequence. Maybe James does this.
That's
right?
what I had in mind, actually. So yeah.
Yeah. So, and maybe if James chooses to behave like random noise, then that might work. But there's no reason for James to do that, and the scheme should work regardless of how James behaves, as long as James respects the power constraint on himself. Right. So James cannot violate, for example, the number of bits. Okay? So it truly is worst case in that sense. So just coming back to this example. So over here, in this example, it's a bit flip channel. So it's a state deterministic channel. So the channel output in this example is a deterministic function of the two channel inputs, X and S. Alice has, in this example, maybe some input constraints. So her code words can be at most NW1s in them, okay, let's say. Let's say James can flip at most NP bits. So these are just examples of some such constraints. This is what I'll call an adversarial binary symmetric channel, or maybe more precisely, an adversarial bit flip channel, right? And this is just one example of potentially many, like infinitely many different adversarial channels. Okay. So going forward, so yeah, these three things determine a channel. So I'll denote an ABC problem, an arbitrary varying channel problem, or a noise, or a an adversarial communication problem by this triple, by this W, lambda X, and gamma X and lambda S. So these three things will determine what's going on. And like some technical remarks. So two things. In this talk, I'll only focus on symbol-wise state deterministic channels. So what do these things mean? So symbol-wise means that the ith channel output depends only on the ith channel inputs. So here, so for example, in that adversarial bit flip channel before, yi is xi XORed with si, right? Now note that this s vector, this s itself could depend on previous previous xi's. Like James, when choosing his jamming sequence, can choose his jamming sequence based on the full x vector. So that's not the problem, right? It's just that the transition from x, s to y, that should be memoryless. That should be symbol-wise. So that's what the symbol-wise over here means. Okay, it doesn't actually mean that the noise is memoryless. Not the noise in general. Like in general, James will want to use something with memory. Okay? So a slightly subtle point that I wanted to emphasize. Now, a non-example is deletion channels. Like for example, if a certain bit gets deleted, then the ith channel output then depends on the i+1th channel input, right? So deletion channel is not an example of this, and therefore I will not be able to say anything about adversarial deletion channels. One specific example. There are others, of course, like intersymbol interference channels and so on. So we cannot say anything about those. Okay, but a fairly large class of channels we can say something about. Okay. Now, another thing that is more technical, and actually we can say something, but it just becomes more distracting, so I will choose to not talk about it, is a non-state deterministic channel. So I'm choosing to focus on state deterministic channels, where the ith channel output is going to be some deterministic function of the ith channel inputs, xi and si. Now, actually, you could imagine something where the ith channel output, yi, is equal to xi plus si with some probability, and the flip of that with some probability, right? You can imagine some extra noise being added to the whole channel output. And in the ABC literature, in the arbitrary varying channel literature, these are also considered as just part of the channel model. And indeed, with some extra effort, even we could consider that. But just to keep things simple, for this talk, I'm not going to focus on that. Okay. So you can think of the channel output being a deterministic function of the two channel inputs, just for this talk. Okay.
So maybe this is a completely trivial remark, but let me ask it anyway. So this includes the set, let's say the standard adversarial setting, in which I can just, so let's say in the Shannon model for the BSC with some probability P you flip, and let's say in the Hamming model, you have a p fraction of things that you get to flip, and those are adversarially chosen. So this is a more general model. This is a strictly more general model than that. So I can encode this problem into this.
Exactly. So so that is like this example is already a more general example than the one you talked about, because here I also put in some constraints.
Yeah, and also you have exactly that thing on Alice too.
Right. Yes. So you could choose to remove those constraints on Alice, and then it would become precisely the example you talked about. So again, just to be concrete, here the constraints on Alice and James are indeed state constraints, are indeed type constraints, right? The fractions of ones in their vectors are at most something, right? So it's a constraint on the empirical distribution of the vectors in their sequences. So that's an example of the type of power constraint. So we'll restrict
So on Alice, I can also think about this as a constraint on the codebook itself. So this is essentially restraining me from using some types of codebooks.
Indeed, indeed. And if instead of binary alphabets, for example, if you had ternary alphabets, you could imagine having, for example, I don't know, L1 constraints on these things, or more, more general constraints, not just necessarily Hamming weight constraints. You can have very general constraints over here, as long as they're functions of the types. Okay. All right. All right. So these are the classes of channels I will allow, and hopefully based on the discussion we just had, it seems like people are comfortable with the fact that it's a fairly general class. So again, the channel problem is dictated by these three sort of this channel law and these two sets, right? And Alice and Bob have to pick a codebook, have to pick an encoder and a decoder, right? So that's what Alice and Bob have to do. James, after knowing this encoder, decoder, and knowing everything about the problem, like these parameters, can choose a particular, and also knowing the actually transmitted code word, like nothing is hidden from him, can then choose how to jam a particular sequence S, right? Now, a few remarks. It turns out using private randomness at any of these parties, Alice, Bob, or James, doesn't actually help. So actually, it'll turn out to be the case that I'm going to sort of skip over some things here, but basically, it turns out that there's really no probability hidden anywhere in this model. Like, if you demand that for every message and for every jamming action by James, Bob should be able to precisely, with zero error, output what Alice had transmitted, then this is as general as can be. If you demanded, like if you tried to relax the problem by saying, well, on average over Alice's messages with high probability, Bob should be able to decode, still is essentially the same rate is obtainable. So there are reductions showing that the relaxed version is actually really the same as the original version, and so on. So really, you can just view this as a combinatorial problem. You can view this as a combinatorial problem where it's a zero error problem, where for every message and for every jamming action, Bob should be able to decode with zero error. Okay, and very roughly, the reduction basically goes around by saying, well, if you could achieve a high probability of success, then really there must be just a few messages and corresponding code words which are problematic. You may as well throw them away, and then you must be left with a clean code book which is not somehow corruptible. Okay, so I'm not going to dive into that reduction in detail, but you can maybe imagine how you can clean up a high probability code book to get a zero error code. Okay, so
but this wouldn't work for like point-to-point or Gaussian channels. So I'm a little bit.
So if you could imagine a point-to-point bit flip channel where someone gives you a guarantee that no more than NP bits are going to be.
Okay.
Then this is exactly that. Or a quadratically constrained channel where someone guarantees that the L2 norm of the vector added is no more than square root of NP, then this would be exactly that problem. Okay. All right. So that's why in this case, we can just ignore the probability of error, and the metric of interest will just be, if we cared about the capacity, then it would be the supremum of the coding rates, which would be achievable under something. All right. So in this talk, now that's a hard problem. Characterizing capacity is hard. Even in that bit flip example I talked about, It's been open for like essentially 50 years at this point. So I do not aim to characterize the capacity, but we will, by the end of this talk, understand strategies that will tell us exactly when a positive rate is possible. Okay, not just for the bit flip channel, which has been known classically for a long time, but for any channel within the class that I talked about in the previous few slides. Okay, where you have a very general channel input-output relationship and constraints on the inputs and the noise vectors. So it's sort of like a coarser version of Shannon's problem. Shannon was able to tell us precisely the rate for random noise channels. Instead of telling you the rate, I'll be able to tell you when a positive rate is possible and when it is not. And there's a dichotomy theorem.
But okay, let me ask one more question here. So
yes.
Here I should think that n goes large and then I want to achieve a fixed positive rate?
Yes. So
because I think that yeah, so for example, for the error thing, I'm not sure there is any positive thing, no?
So let me just show you actually, the bit flip example. So in this case over here, like this is, I'm sorry, some of these slides, the font is a little bit small. Hopefully you can see it. Not really. I mean, it's okay. You can see it. So this is just a bit flip example, like that bit flip example we talked about earlier. And if it was random noise, we know, of course, the Shannon capacity is 1 minus HP, right? So this is just the 1 minus HP curve. But if it's adversarial noise, if James can flip a quarter of the bits, if James can flip more than a quarter of the bits, so that's like saying you want the minimum distance to be larger than n over 2, right? Then there's a constant number of code words you can pack in, and therefore the rate goes to 0. Note that it's not that you can't pack any code words, but there's only a constant number of code words you can pack. And since this is independent of the block length, so therefore the rate goes to 0, right? This constant number of code words, note there's no n over here. On the other hand, if you back off even a little bit, if you only demand, so if James can flip strictly less than half, can flip strictly less than a quarter of the bits, so the minimum distance only has to be slightly less than a half, like n over 2, then indeed there are ways of packing exponentially many code words here, and therefore a positive rate is possible, right? Now that rate will depend on this epsilon back off. So if you want to be really close to this quarter, then the rate will be small, but nonetheless positive. Okay. So
thank you. That's exactly what I was asking. Thanks.
Okay, good. Now, actually, for this particular problem, for this bit flip problem, even the rate of approach to this 1/4 is open. Like it's somewhere between 1 over epsilon square and 1 over epsilon square log 1 over epsilon. So that log 1 over epsilon factor is open as far as I'm aware. Okay. So even the derivative here is unknown. The derivative here is unknown, and so on. So there are interesting questions. Okay. So up to even ignoring constant factor. So the function. All right. So you can see that demanding these hard packing, demanding that there be no overlap between these noise balls, makes a drastic difference in terms of the threshold where a positive rate is possible and the rate where a positive rate is possible, right? Like compared to the nearest apples to oranges comparison between random noise and adversarial noise, there's a drastic difference, right? In terms of behavior. The Shannon noise case, fairly well understood, right? Like we know the capacity, but not just that, we know how to design good codes. We worry about, near linear time codes. We worry about like so many implementation issues. Here, even the capacity is open, right? And let aside computationally efficient codes. Okay. All right. So yeah, so the best upper bounds are like the LP bound. The best achievability is still the Gilbert-Wasserman bound from the 50s, right? So this is really it's a very hard problem. All right. So what is this talk about? So I spent around half my time just talking about the previous stuff. So when I say Shannon-style results for adversarial noise, again, the capacity is out of reach. We do not aim to do that, though we do get novel achievabilities and converses, but we don't aim to actually get a tight capacity characterization. What we care about is just that coarser question about the rate positivity, right? So it's like a 0th order capacity characterization instead of a 1st order capacity characterization. Okay. All right. So the slide is a bit dense, and but just to parse it a little bit. So again, this is tied to what I talked about earlier. It's just an expanded version of that system diagram. So there's a very general input alphabet and some power constraints on the input code words, like these are type constraints. So the histogram of these code words can be arbitrary. Arbitrary within the set. James similarly has an arbitrary power constraint, like type constraints on his noise sequences. And then there's a symbol-wise channel that combines these two to generate an arbitrary output alphabet. Again, the noise sequence can depend on the code book and the transmit code, right? So a fairly large generality. And the main result is a precise characterization of this transition. And again, just to drive it home, so that example we saw before, where there are constraints here, NW, the Hamming weight of X is at most NW, the Hamming weight of S is at most NP. So this has been classically known. This is not new. We can recover it, of course, but it was known classically that the phase transition is P is equal to W minus W squared. Okay, it's a consequence of a slight generalization, or well, like Johnson bound plus the GV bound together, you can get this. But for example, you could tweak the problem. You could have some more general input alphabet, state alphabet, some crazy channel law. There's nothing special about this channel. I just sort of pulled it out of my ass just to write something here. And then you could put some L0 L1 constraints here, L0 L1 constraints here, right? And even here we can give a constraint. It's a little bit more. It takes more effort to compute, but it can be computed. And it's again a packing problem. It's packing now different types shapes into a different type shape over here. So I mean, it's not necessarily pentagons. I just drew it for reference. So it's generally speaking, these are basically how many, as the subtitle of the talk said. So how many of a copies of a high dimensional shape can you pack into a different high dimensional shape, right? Roughly speaking, that's the flavor of the question that we aim to answer over here. Okay. All right, so now let's get into proof sketches in the remaining 25 odd minutes I have, and we'll see how far we get. So I hope we get reasonably far. Okay. Any questions before I move on? Okay, people have been proactive in asking questions, so that's great. Oh, hi, I just saw you, Anand. Good to see you. All right. Go. All right. So the first idea is just a standard one, which is a so-called reduction to constant composition code. So what does that mean? So suppose someone gives you a code book, which is some length n collection of vectors over some alphabet script x to the n. So let's color each code word according to a type. So again, what's a type? It's the histogram of the code word, the vector's empirical distribution. So for example, if this vector here is blah, then the fraction of 1s is 3/8, the fraction of 2s is 2/8, and so on. So those are the types, right? So just color them differently according to their type. And then choose the largest constant composition subcode. So what is that? Well, in this figure here, maybe there are more green code words than anything else. So because of fairly elementary counting arguments, the number of types is at most polynomial in the block length. Therefore, the largest constant composition code is at least the size of the original code divided by some polynomial in n, right? So if you had an exponential size code, you'll still have the same exponent size code essentially for the first order an exponent. You don't really change the code rate by choosing a constant composition code, right? So it'll make life simpler just to think in terms of all the code words being identical in terms of type. Okay? By choosing a subcode, you only make it harder for James to confuse code words, right? So doing this reduction doesn't make it easier to confuse it. So if you have a good code to begin with, by doing this operation, you still have a good code, and it's still essentially the same size. So we may as well work with that. Okay? Yeah, and the rate is essentially the same. All right. So now some more definitions. So in this example, let's say you have two code words with the same type. So both of them have this particular type over here. So a self-coupling is just another name for joint type. So in this example, the fraction of 0 ones is like the 0 1 pairs is 3 over 20. So that's this entry in this matrix. And of course, this 4 by 4 matrix, it has many different entries corresponding to all pairs, right? So that's a joint type. And this is what I'll call a self-coupling, because it's a joint type where the marginals on x and x prime are the same, right? That's because we chose two code words with the same type. So that's like saying that the row sum and the column sum of this joint PMF is the same. It's precisely this P of x over here. Okay? So there's nothing really new so far, but it's a special type of joint PMF that be of particular interest, because after all, we're restricting ourselves to code where every pair of code words have the every code word has the same type, and therefore we're restricting ourselves to joint types like this. Okay. Now, one very useful feature of these joint types, of these self-couplings, is that they embed within them the distances. For example, so suppose we wanted to compute the Hamming distance between this pair of code words. We could, of course, literally just count the number of locations where they differed entry-wise, right? But you could also think of taking this self-coupling matrix corresponding to this and taking an inner product with a special matrix, the C sub h, h for Hamming, which they have zeros along the diagonals and ones everywhere else. So if you view this matrix as a vector, if you view this matrix as a vector, take the inner product vector-wise, or the Hadamard product of these matrices. So what you're basically doing is you're zeroing out the diagonal elements, the elements corresponding to these two vectors being the same, and you're just adding together the off-diagonal elements where these vectors differed. So literally, it's just a bookkeeping trick, a different way of computing the Hamming distance between this pair of code words, right? So all of this is a long-winded way of saying that you have a given this matrix, you can compute the Hamming distance between the pair of code words with this joint type. Right? But you can do more than that. If you were interested in the L1 distance between the pair of code words, you could change the corresponding matrix to something like this. And then you can convince yourself that you can actually compute the L1 distance between pairs of vectors by taking the vector-wise inner product of this matrix and this matrix, just by changing the formula. Right? So really what this is saying is that these matrices over here encode within them very general distance metrics. So the self-couplings, in fact, not even just distance metrics, pseudo distances and so on, like all of these can be encoded within the self-couplings. Okay, and that would be a useful fact, which we'll see later. Salim is looking worried for some reason. I'm happy to take questions. But yeah, it's just, I don't think I've said anything particularly deep here, but I'm just trying. All right, so these matrices sit within, I mean, these are joint PMFs, right? They're joint PMFs on script x by script x alphabet. So they sit within a script x squared dimensional space, and you can think of the simplex in that space, right? So these are basically just script x by script x non-negative matrices with entries add up to 1. So you can just think of them as being within the simplex here. Okay? And since we require that the row sums be equal to the column sums be equal to some p of x, so those just add some additional equality constraints on these matrices. So then you can think of them as being within some polytope over here. So this is some JP of x. Okay? So someone has told you, I want, for example, ternary codes with a pre-specified type, where every code word has a pre-specified type. Then you could imagine writing down a set of polytope constraints which would define the polytope where this. Okay? All right. So now let's look at specific examples of such matrices, which will shed some light on what's going on here. So, for example, you could think of the diagonal matrix, where the diagonal entries are precisely the entries of P of x. So your P of x type, put those entry-wise along the diagonals, put zeros everywhere else. So this is certainly a joint PMF, right? Because the entries add up to 1, they're non-negative, right? And the row sums are equal to the column sums are equal to P of x. So this is a self-coupling, right? Because it satisfies all those constraints that we have. Similarly, this rank 1 matrix corresponding to the outer product of the P of x column vector with the row vector is also a self-coupling. I mean, again, you can convince yourself it's a joint PMF, the entries are non-negative, add up to 1, and the row sums are equal to the column sums are equal to P of x. Okay? So so because of this, both of these are self-couplings. Both of them are within that same space, the P of X space. Now this first one is actually a terrible idea for code design, because what does this correspond to? It corresponds to having two identical code words, right? X is equal to X prime. So if you have two code words which are identical, the joint type is exactly this diagonal matrix. But if Alice has two identical code words corresponding to two different messages, then there's no way that Bob can distinguish whether message M1 was transmitted or message M2 was transmitted, right? M or M prime was transmitted. And therefore, you don't really want to code with some self-coupling like this in your code. Right? On the other hand, as information theorists or coding theorists, we are used to using this product distribution all the time. So what do I mean by that? So suppose you choose a random code with, say, some positive rate, let's say 2 to the epsilon n code words of length n, where each entry is drawn IID according to P of X. Then if you think about it, the expected joint type between the pairs of code words is exactly this product distribution, right? Because the fraction of, for example, the fraction of pairs where you have I in X and J in X prime is approximately, the expected number is actually Pxi times Pxj, right? That's the expectation. And then just by a concentration of measure arguments with high probability, the actual joint type for a specific pair of code words will be pretty tightly concentrated around the expected joint type, right? And then if your rate is sufficiently small, if your epsilon is sufficiently small, then in fact, all code words, like just a very crude counting argument, so all types will be tightly concentrated around here, right? So a random code, or at least a random code with expurgation, you can tightly concentrate things over here. So really, it will be as if this will behave. If you wanted to think of it geometrically, like every pair of code words have roughly the same joint type, or if you wanted to think of it geometrically, kind of like a regular polytope, right? Somehow, if you mentally replace joint types with distance, then it's kind of like a regular polytope, roughly speaking. Right? And indeed, you can formalize that intuition in a certain way, but I'm not going to go in that direction. All right. So we're used to thinking of random code, but is that really all we can do? Well, you can certainly think of generalizing this by saying, well, different coordinates. So in your n-length code words, I could choose the first few coordinates according to one distribution, the next few coordinates according to a different distribution. I can certainly do that. I can even do more than that, right? But at least I can do that. So just to be concrete, you could imagine like the first n by 2 coordinates sampled according to a product distribution, say half 0, right? So this corresponds to only choosing. So suppose your alphabet is let's say A, B, C, right? You have A's, B's, and C's. So in this first n by 2 coordinates, you're only choosing A's and B's equally likely, right? And then the next n by 2 coordinates, you're only choosing B's and C's with equal probability, right? So that's what you could do in something like this. And then your overall joint distribution would then be the convex combination of this rank 1 distribution with this rank 1 distribution. So it would look like this. So the overall joint types of A's, B's, and C's would look like this. Notice you would not have any A comma C pairs because of the way you constructed it, right? But that's what your joint types would look like. And again, all joint types would be so if your rate is sufficiently small, all joint types would be tightly concentrated around the center with high probability. And these convex combinations, this convex combination of product distributions, are precisely what are called completely positive distributions, or completely positive self-coupling. Okay? So at least we did get to the point where I was able to reference being completely positive, right? And therefore, I declared success in getting to the pun. These completely positive distributions are actually a slice of the so-called completely positive cone, which has been studied in convex analysis. And really all we've been able to, so based on what we just said, we've basically said that if someone gives you a completely positive distribution, like a target distribution, which is a completely positive distribution, you can generate a code where every joint type is like that completely positive distribution. Okay. Now, so far I've just talked about it from a code design perspective without yet really talking about the channel at all. But again, I see people looking a bit pensive. I'm happy to take a question or two before I move on. Any questions? Okay.
I have a
right.
question. So
yes.
So I guess I have two questions. So the ultimate goal is that you wanted to show that there is a phase transition, and that's what you want to prove in the end. That's the result.
That is the goal. Yes.
Okay. And then and here, so this kind of result. So what do you need it for to prove that the ultimate result? So you want to have you have a target joint distribution that you want to achieve.
Okay, so far it must look all very mysterious because I haven't shown anything. But basically the phase transition will happen depending on two geometric objects. When one geometric object, which is this completely positive distribution, fits within another geometric object, then essentially nothing will be possible. Otherwise, something will be possible. Okay, so we're heading there. So this is so far just at the phase where we are defining things that will be useful later.
Okay.
Good. Yeah, thank you. Yeah, I forgot to give a higher level overview as to where we're heading, right? But it's like someone saying, "Mommy, are we there yet?" We're far from being there. Yeah, we'll get. All right. So the other object, to define that other object, let's ask about this question. Let's think about this question. So far we've talked just about generating random code with some target distribution. We haven't really talked about the channel. So what about the channel? So first of all, suppose someone gives us a pair of code words, X and X prime, and asks, can James confuse Bob about whether X was transmitted or X prime was transmitted? Okay, so that's what we'll call confuseability. And what does it mean for James to be successful in confusing Bob? It means that there are corresponding jamming actions. So if X was transmitted, then James should be able to choose some jamming vector S. Whereas if X prime was transmitted, he should be able to choose some jamming vector S prime, such that under the action of the channel, W on both of these, you end up with the same Y, right? So like think of that bit flip example. If for two different code words are corresponding different jamming vectors such that you result in the same Y, then these two pairs of code words will be confusable from Bob's point of view, right? So that's what it means for a pair of code words to be confusable. Okay? Now, here's a very important property. Confusability is permutation invariant. What does that mean? So if a pair of code words is confusable, then if you permute the coordinates of X and X prime according to the same permutation pi, they'll still remain confusable, because what can James do? He can permute the coordinates of S with the same permutation, and then it will result in a Y with the same permutation, right? That's because the channel is acting symbol-wise, right? So what this is saying is, like, confusability is actually just a function of the joint type. Okay, and this, by the way, is where we are intrinsically, importantly, using the property that confusability is a function of the is symbol-wise. So the deletion channel, for example, fails over here because if you permute things, then this property no longer holds, right? And I think it's a fascinating question to think about the problem with deletion channels, but we don't know how to handle that. But basically because of this property over here. Okay. All right. So now confusability, you can prove various other things about confusability. For example, it's a convex property. So for example, if a pair of code words is confusable, another pair of code words is confusable, and so on. So these K tuples of code words are confusable. Then you could imagine like a mega code word here and a mega code word here, which are therefore also going to be confusable by the corresponding, mega actions S1 to SK and S1 prime to SK prime, right? So what that's basically saying is that the convex combination of these joint types of X1, X1 prime, X2, X2 prime, and so on, that's also going to be confusable. So it's really just a time sharing argument. It's basically saying confusability is convex in the joint types that are confusable. And you can prove various other things. Now this slide, I do not intend people to digest on the fly, but basically what it's saying is that you can write down as a system of linear equalities or inequalities corresponding to confusability. So checking for confusability is computationally efficient. It basically comes down to writing some linear constraints. Therefore it's checkable. It results in a polytope. So overall, like, in this space over here, in the space of joint types, the confuseability set, the confuseability polytope is I'm going to write it as this script K, okay? And it's convex, it's transversely symmetric, it's efficiently computable. Like there's a bunch of properties you can write down about it. But the key takeaway over here is that really there's a forbidden region. Like think of this brown or maroon region as being forbidden. If you want for a given channel to have a good code, then all joint types are forbidden from being within this K object over here. Okay. So for example, in the Hamming distance case, think of the Hamming distance as being a polytope. You can actually write down the Hamming distance as a slice of this original polytope, and the corresponding joint types should all be outside that Hamming distance. Okay. All right. So now we know two things. We know that yellow object of completely positive distributions. We know this maroon object of the forbidden region. So now we can begin to put these together. Okay, right. So actually, before I go there, so let me also make a couple of other remarks, which will be interesting. Okay, yeah. So it turns out you can have you can construct two ABCs, two adversarial communication problems that look very different. For example, they can have different output alphabets and so on, but they can have the same confuseability polytope. But if you have a good code for one, then automatically it's a good code for the other, right? If you have a code where every joint type is outside the forbidden region here, then it's outside the forbidden region for the other. So what that says is that this confuseability polytope precisely characterizes not just the capacity, but the goodness of a code for an adversarial communication problem, right? So it's a fundamental invariant of a adversarial communication problem for state deterministic ABCs. A subtle point is that this is not true if you have some additional random noise. So like that example I talked about earlier, where you have some additional random noise, non-state deterministic ABCs. So those things can change. But again, just think of it as a technical remark. Don't worry about it. Okay. For the purposes of this talk, you can think of this K as being a fundamental object that characterizes the capacity and the goodness of a code and so on for a particular adversarial communication. Okay. All right. So now we have these two geometric objects. So now I can at least get to sort of the main theorem statement that one half of which is much easier to see. The other half I'll try to sketch. We'll see how far we get. I don't want to overrun drastically. Of course, Sareem can control the time and we'll see how far we get. But basically, if there's something completely positive that sticks out over here, so if you have something yellow, remember something yellow is completely positive, and we said that if you have a target distribution that's yellow, you can generate an exponentially large code such that all joint types are close to that target distribution, right? So if there's something yellow that sticks out of the forbidden region, you can have a positive rate. Okay. In fact, if you care to characterize it, there's a Gilbert-Bashmov type rate you can achieve, or you can even achieve, like if there's something yellow that's not a product distribution, then there's a more complex GB type thing that you can achieve. So you can give certain achievable rates over here, and it comes down to trying to understand large deviation exponents and so on. So this is relatively standard. Okay, I mean it's novel in the sense that people hadn't thought of it before us in this particular way, but the actual techniques are not that complicated.
Sid, in terms of like tractability and complexity, how hard is it if you don't have any? Well, here you have a discrete alphabet, but I mean.
Yeah. So if someone gives you a particular P of X, then computing the corresponding these types of rates for the GB thing, you can do a Blau-Taramoto type algorithm and you can actually compute it because it turns out to be a complex thing. Which is not to say that there aren't other interesting complexity issues, but I'm not going to go there. Right? But that's a great question.
But I mean, so I have another question. So for Blau-Taramoto, right? You can achieve the. I'm just trying to. Maybe it's a paranoid question. So you achieve the capacity within an epsilon because it's a numerical method. But maybe this epsilon is what's going to characterize whether your capacity is positive, whether your rate can be positive or not. Is that a thing? Something that it should work out?
Right at the boundary, you're going to have trouble. But if you take like the complexity of Blau-Taramoto, if you want your epsilon to be sufficiently small, then the complexity scales as some polynomial in 1 over epsilon. So if you're willing to pay enough time, then you can get there. Actually, a much bigger issue is that if your alphabet size is sufficiently large, like the CP set, even though it's convex, the complexity of characterizing the CP set is exponential in exponential in the square of this alphabet size. At least the best known algorithms run that way. So, you know, small alphabets 2, 3, 4, 5, actually up to 4, there are computationally efficient algorithms because you can write it as a positive as a STP. But 5 and beyond, then the best algorithms we have scale as 2 to the alphabet size square roughly. So there are other bigger issues than just that alphabet size. Okay. But yeah, there are certainly many interesting issues here to do with computational complexity. Okay. All right, but anyway, so far this is just the achievability side, right? The main part that I've hidden under the rug so far is the contrapositive, which is what if the thing looks like this? There's nothing yellow poking out of the forbidden region. In this case, and this is the main technical part of the proof, this is a so-called generalized Plotkin bound that we believe is normal, relying on some convexity arguments. On some combinatorial arguments. Okay, so I'm clearly getting close to the boundary. So Salim, how much time do I have? I suddenly lost you. I just heard and then I didn't hear anything.
So how about 10 more minutes?
10 more minutes, good. So I can give.
How much time do you need? How much more time do you need?
Let's say, by the way, this is misleading because I've merged slides from different things. So this is misleading. But 10 minutes would be good to give you a flavor.
Okay.
All right.
And I'm hoping also Anand will ask some questions at the end because he's also an expert in this.
We talk about this. We usually talk at 9 a.m. on Fridays, like every week.
But maybe for people,
I'm enjoying the like slower down pace of the description because I understand things better now.
All right. Yeah, we have a long-running adversarial meeting, so which other people are welcome to crash whenever they're interested. So, okay. So before we dive into the generalized Plotkin bound, as a guidepost, let's look at the classical Plotkin bound. Let's see a proof that I actually stole from the class notes of Andrei Bogdanov, my colleague here at CUHK, which is this is a single slide proof, which I think is quite nice. It's a geometric proof. So the basic idea, this is the classic Plotkin bound. It's just for binary code Hamming distance metric. You can generalize it significantly. Indeed, other people have for general alphabets, more general metrics. So people have done that. But nonetheless, let's first focus just on binary code. So suppose you have a binary code and you demand that the minimum distance of the code be strictly larger than n by 2. Okay, so n by 2 times 1 plus epsilon for a positive epsilon. Then the Plotkin bound tells you that a direct consequence of the Plotkin bound is that the size of the code is a constant independent of the Plotkin. And how does the proof go? So first of all, you map these binary code words to plus minus 1 code words. And then like a little bit of algebra tells you that if you demand that every pair of code words have a sufficiently large minimum distance, like sufficiently large pairwise distance, then that's the same as saying that the inner product of these code words over the plus minus 1 alphabet, must be negative, must be smaller than minus epsilon n. Okay? And really, it's just a shifting, rescaling, and then you just do the algebra, and you get the fact that this is negative. What that means is that you're demanding that every pair of code words makes an obtuse angle with respect to each other. And now, if intuition has any guide, like that feels like a hard thing to demand, right? Like if you demand that you want a large number of code words such that every pair is obtuse, there can't be too many of them. And to formalize that, here's a one-line proof. So you consider the specific quadratic form, which is just add together all your code words in your code book, these plus minus 1 code words in your code book, and then take the inner product of this vector with itself. So firstly, since it's the inner product of a vector with itself, it must be non-negative. That's the first inequality, right? Then you break this up into a self-product term and a cross-product term. Self-product just means inner product of a vector with itself. So again, it's going to be non-negative, right? But there are at most C such terms. Every term is everything here in this X vector is plus minus 1. So it's basically, in fact, exactly equal to NC, right? So because these are n-length vectors, every coordinate is plus minus 1. So it's exactly equal to NC. But then here you have these cross product terms. X in a product with X prime, where X prime is different, or this should be a X prime, the prime missing here. So, and since we know that every X prime in a product is negative, is minus epsilon n. So now you have many more, like C square roughly in a product terms, each of which is negative, right? So you have something slightly positive, NC, but you have something much more negative, minus epsilon n times whatever. So when you do the math, if your C is larger than order 1 over epsilon, then you have a contradiction. You have 0 is less than or equal to something negative. That's a contradiction. And that's the Plotkin model. So if your code is too large, impossible is Plotkin, right? And that's it. Okay. So how do we generalize it? We have to try to mimic it. And to try to mimic it, there's a few ideas that will be useful over here. Okay. But before I go on, any questions about this classical Plotkin model? Yeah, this is a little bit different than the one in Wikipedia. I view this as interesting, like as a perhaps more intuitive, certainly more geometric than the Wikipedia. Okay, so in the generalized Plotkin bound, the two important ingredients are firstly some Ramsey theory to extract a subcode with some properties, okay? and then some duality, which will try to replicate that previous analysis that we did earlier. Okay, so I'll zoom through both of these in the next 8 minutes. I mean, I have some pretty pictures, and hopefully those will highlight the basic ideas. Okay. All right. So firstly, this Ramsey theory idea. So look, suppose someone gives us a code. So what is the goal over here? The goal over here is if you have something like this, like the forbidden region entirely contains this yellow region, completely positive things, then you can't have a very large code. Okay, and we'll prove it by contradiction. So suppose someone gives us a very large code, an exponential size code. So all pairs, all joint types are outside this forbidden region, right? They have to be, because if they're inside this forbidden region, James could confuse them. Okay. So now think of these code words as being vertices of a graph. Okay. And think of pairs of code words as being edges of this graph. So for example, this pair of vertices has a particular joint type. So maybe it's in this region. So I'll color it like yellow or orange or whatever this color is. Okay. This pair is somewhere over here. So I'll color it red. Okay. And basically, if code words are close enough, like if joint types are close enough, then I'll color them roughly the same color. Otherwise, I'll color them different. Okay. So these edges are basically joint types. Okay. Or to be more precise, they're like quantizations of the joint type. For technical reasons, I can't really color them according to the joint types. There are polynomially many joint types. That's too much. So instead, I quantize it. But that's sort of a technicality. Okay. Just
so how many values do you quantize them?
So that there's a constant number of quantized values. It's possible to do this such that like you can cover it with some epsilon balls, and a constant number of these epsilon balls turns out to be sufficient.
And these quantization levels determine the colors of the edges. That's what.
Yeah. So it turns out that there's a constant number of colors, and everything with the same color is epsilon away from each other in terms of joint types. Okay. It's possible to do this. You can take my word. Okay. The number of colors is a it's an exponential function in 1 over epsilon, but that's still a constant, right? Exponential in 1 over epsilon is still a constant, large constant, but nonetheless a constant. Okay. So now I have this graph over here, and what Ramsey theory tells me is that given this original graph, there must be a clique with the same color. Okay, so like you've probably seen some version of Ramsey theory before, friends and enemies, and there must be at least in any group of 6 people, there must be at least 3 who are friends or enemies, right? So there are generalizations of this to multiple colors. And basically a consequence of that is that any sufficiently large code, any exponential size code, must have a quote unquote large, it's actually not that large, but large enough for our purposes, a sufficiently large subcode where every pair is roughly the same joint type. Okay. So what this does is it imposes some structure on the code that someone has given us. A priori, all that someone told us is that there was a code where all joint types are outside this forbidden region. And now we have deduced that within this code, there must be a subcode such that it looks like, it looks like it's sort of coming from the same joint types. Every pair is coming from the same joint type. Okay, as a consequence of Ramsey theory. Now, again, this is a very inefficient reduction. Like in general, this will be polylog size of the original code if you use Ramsey theory, and there are open questions as to reduction and so on. But nonetheless, this is sufficient for our current purposes. Okay, that's the first step. The second step, this duality theory, is okay. So what do we have? We have like this p hat is an approximation to all these joint types outside CP. So the second step is this duality. So again, like I promised 10 minutes, I have like 3-4 minutes. So let me just highlight that. So this duality theory says the following. So let's define one last new object here, one last definition. So this is the set of co-positive matrices. So what are co-positive matrices? They should remind you of positive semi-definite matrices. They look a lot like positive semi-definite matrices. Again, there's a typo here. This should be X, Q, X transpose or something like that, right? Or X transpose QX. But basically, it's saying that if you have an entry-wise non-negative X, then you require this. So it basically is a relaxation of positive semi-definite matrices. You require this to be non-negative only if X is entry-wise non-negative. Right? So it's in general a larger cone. It's a larger convex set than the set of positive semi-definite matrices. Okay, so this turns out to be a convex cone of matrices, and we'll call it co-positive matrices. And it's known. So the set of completely positive matrices you've already seen before. I've reparameterized it here. Don't worry about the reparameterization. But here's the important thing: Hall and Newman showed in 1963 that CP and CoP are dual. Okay, and dual just means the inner product. So if you view these two matrices as vectors, inner product of a CP matrix and a co-positive matrix is always non-negative. Okay? So this duality will be very important. It'll be related to that quadratic form that we talked about. All right. So what that means is, if you have this p hat which is not CP, right? Remember we had extracted this p hat which is not CP over here. So if you have a p hat which is not CP, then you can find a co-positive witness. You can find a Q matrix such that the inner product between this p hat and Q is negative. Okay, you can do this. And because you can do this, so now we can try to tie it together with that Plotkin bound idea that we had before. So you consider a different quadratic form, and the credit for all of this goes to Andre, my colleague here. You consider a quadratic form comprising of all joint types within your extracted subcode with this Q matrix. Because of co-positivity, I'm not going to go into why, but just because of co-positivity, it turned out to be non-negative. You just have to squint at things the right way, and it's not complex. It's a half page of algebra. You can get this. And then you do the same trick as before. You split it up into self-product terms, cross-product terms. The self-product terms are bounded in magnitude. It really is like the Plotkin bound we saw earlier. Okay, so this is bounded magnitude, not too many of them. These are cross-product terms. They're all negative, and there's many more of them. C square of them, right? So therefore, you have a few positives, lots more negatives, and they add up to something. So if your code is too large, you have a contradiction. Okay. So the proof is really reminiscent of that geometric proof earlier. But what you had to do was replace the ideas of inner product of code words with this more general quadratic form over here, and then you're able to replicate that proof using ideas of duality. So that's really it. Now, I've hidden a whole bunch of technicalities under the hood over here. There's an important part because for asymmetric matrices, it turns out very recently we discovered due to Formlosch, which we can use to simplify the arguments and so on. But here's a punchline. The punchline is, on the one hand, so for any adversarial channel, either the picture looks like this, exponential size packings or constant size packings, and which side of this line it falls in is precisely given by either the figure looks like this or the figure looks like this. Okay? Either the forbidden region contains the completely positive set, or the completely positive set is outside, at least as part of that, which is outside the forbidden region. And that's the punchline. There are many extensions. You can, instead of looking at pairs of code words, you can pairs of symbols. pairs of random variables. You can look at k tuples of random variables or code words, and then there are list decoding results corresponding to tensors. You can come up with outer bounds based on generalization of Felius-Pascal type bounds. You can generalize to those non-state deterministic, like you have additional random noise. So you can also do weird things like, so given a forbidden region, you can reverse engineer adversarial channel with that as a polytope. You can use these to prove results about other ABCs as well. So not just these omniscient ABCs, that the adversary sees everything. You can do things with myopic ABCs, like adversary sees a noisy version of the transmission or sees a causal version of the transmission. You can get some sort of results there. And there are connections which are beginning to explore to error exponents, mismatch decoding, and so on. Okay. So that's it, as we say here in Hong Kong, doje, or in mainland China, xie. Thank you.
Thanks a lot. So this was very interesting. So I don't know. So I'm going to clap on to use fully the Zoom. I'm going to clap on Zoom so you can see next to my picture.
All right, I see that. Thank you. Appreciate that.
So I don't know if anyone has questions. So I don't know what Anand's doing, but we cannot hear you, Anand.
I'm trying to eat the hand because it was there.
Oh, okay. So I don't know. Does anyone have questions? So I think we asked enough questions. I don't know if someone has a question or comment or I don't know.
I guess. Well, I guess for the CP tensors that you just talked about at the end,
Yes.
What's the corresponding condition? You want to have a three-way outer product that's.
Sure. So if your k-wise distribution, so if you have a k-wise distribution,
Mute yourself, Anand.
testing.
It might be Sid's iPad.
Suddenly, I don't know. Well, let me disconnect my iPad, and then hopefully it doesn't me. I can also put on my.
It's working now.
Okay, so somehow it was my thing. Let me just put on headphones. Somehow they started acting up. But okay, so to come back to Anand's question. So if you have a k-wise distribution, P of x1, x2 up till xk, if you can write it as a convex combination of a product distribution, like P of x1, P of
it's
x1.
Got a CP, it's got a CP decomposition.
It's got a CP decomposition, like a convex combination of a rank 1 tensor, a rank 1 tensors.
Right.
Yeah.
Okay, but the copositivity thing is not going to be I guess that was what I was asking about, this copositivity. How do you define it? Because there's not a bilinear form that you can sort of,
right.
Positive semi-definiteness is hard to define for tensors, blah, blah, blah.
Right. So let me just, since I also have my iPad hooked up, so let me very quickly just write something over here, and you guys can see my screen now? Oh, yes. No, you can't. Oh, you can. Did I?
You can see a white screen, but.
Oh, you do see a white screen. Okay. So, yeah, so it basically is saying, like, for example, if you have a P of x1, x2, x3, x4, let's just say, you should be able to write it as summation pu of u. U goes from 1 to some script u. We have alphabet size bounds as well, but let's worry about that later. P of x given u of, so this is x1 up till x4. Should be able to write as x1 given u, P of x given u. So it's the same distribution, but you have different dummy variables. P of x2 given u, P of x given u, P of x3 given u, P of x given u, x4 given u, right? So you should be able to write it as this. So this is just a product distribution, right? This is just a product distribution, and you're taking a convex combination of this.
Yeah, that part I understand. Yeah. I mean, I know what that should look like. My question is, when you said that you have the copositive, the dual,
right.
The dual space, you defined it in terms of this bilinear form, which or this sort of matrix, which was not quite positive semi-definite, but a relaxation of positive semi-definite. I just don't know what the corresponding concept is for.
Right,
for
and
CP.
there is a parallel thing over there for copositive tensors as well, which you can potentially also imagine, right? You can imagine taking for example, for a
three-way outer product.
Yeah, three-way outer product, four-way
Okay.
outer product.
Right. Okay.
Good question. Thank you. I'm sorry.
To conclude, so Sid, if someone is interested in more details, is there some paper or an archive, or is this?
Yeah. So unfortunately, currently what we have is just ISIT paper. It's one of those things where like new results are falling out of the trees every so often. But the student who's been working on this is getting close to graduation, so his thesis will be ready. Well, has to be ready by the summer, and therefore at that point that should be a very comprehensive report. So there'll be that. By the way, the student is looking for postdocs. This is, let me write this down. This is Yihan Zhang. I strongly recommend anyone who's interested in this stuff to consider hiring him if they have money lying around. He's very smart. I vouch for him. Okay.
Okay.
So,
this is great. All right, thank you everyone. So, and if anyone watches on YouTube, they can ask questions on the comments, or they can email you, and